Okay then, welcome to part 4, protection for safety. Now part 4 is responsible for a large percentage of the marks in the exam, and it's a big section, so I'm not going to be able to cover this in just one video. I'm going to split it over 2, maybe 3, possibly even a 4th one. I'm not quite sure yet. You'll have to watch this space for further details. In this one, I want to cover chapter 41. So chapter 41 is the protection against electric shock. The fundamental rule of protection against electric shock is that hazardous live parts shall not be accessible, and accessible conductive parts shall not be hazardous live, either in use, without a fault, or in single fault conditions. And that's actually taken from the electricity at work regulations. So, worth bearing in mind that one. So according to 4.2 of 61440, which is the British standard for protection against electric shock, which chapter 41 is pretty much written around, protection under normal conditions is provided by basic protection. And protection under single fault condition is provided by fault protection. Now we've already covered those two terms before. You're going to see them appearing more and more now as we go through the book. Alternatively, a protection against electric shock could be provided by what we call an enhanced protective provision, which is a protection under normal conditions and under fault conditions. We'll look at those a bit closer as we go on. Each protective measure must consist of an appropriate combination of basic and fault protection. And 410.3.2 states just that in section 1. Alternatively, we can have an enhanced protective provision which provides both. So let's have a look at basic protection. Basic insulation, barriers, or enclosures all form basic protection, protecting from actual direct contact. Now, fault protection is something a little bit different. Fault protection is defined as protection against electric shock under a single fault conditions. So we look here, we've got our CPC cable there protecting a casing. The line conductor has actually shorted down to the casing, so the path of least resistance should be down through the CPC and tripping the relevant protective device. What we don't want is electricity to flow through the human body down to earth. Now, in addition to basic and fault protection, additional protection is required under certain conditions. Additional protection being that of secondary RCDs or a domestic RCD system, as we see in a domestic consumer unit. And under certain external influence conditions and certain special locations, there are certain requirements. Supplementary bonding is also a form of additional protective protection, providing that path down to earth with the least resistance. So what chapter 41 says in 410.3.3 is that each part of installation, one or more protective measures shall be applied, taking into account the conditions of the external influences. And those protective measures are generally either ADS, automatic disconnection of supply, double or reinforced insulation, separation, or the use of extra low voltage. Automatic disconnection then, ADS for short, it's the most commonly used protective measure, and virtually every electrical circuit out there has some form of ADS. ADS being provided by an MCB, a fuse, an RCD, and a path down to earth for any fault current. So let's have a look at a basic ADS circuit then. So we've got one of our phases there from our transformer, feeding a piece of equipment there, and the piece of equipment is enclosed by an exposed conductive part, which is a metal casing. So the metal casing has been provided with a circuit protective conductor back down to the earthing conductor, right back to the distributor's terminals, so it's actually connected to the lowest point of the earthing in the building. So if a fault does occur, if we get a short circuit across live and neutral, the fuse or the MCB would trip. If we get current flowing out to the case, as we've shown here, we've got a current flowing down to the earth potential, at which point an RCD would detect the lack of current flowing in the neutral conductor and would interrupt the current flow. So all exposed conductive parts, metal casings, etc., must be connected to a protective conductor in order for this to work. And in each installation, main protective bonding conductors need to be connected. So any incoming, as we call extraneous metalwork, water installation pipes, gas installation pipes, installation pipe work, central heating, air conditioning systems, any exposed metallic structure of a building, anything entering the building needs to be bonded so that it is all at the same zero potential. Now, for a long time, there's been a lot of discussion over the use of plastic water pipes. A lot of water pipe services, and in fact it was in guidance notes and it was in the on-site guide. It is now finally been put into the regulations that if the service is provided using a plastic pipework or a metallic pipe with an insulated section at the point of entry, then protective bonding is no longer required. Automatic disconnection in case of a fault then. A protective device shall automatically interrupt the supply to the line conductor. The protective device should be suitable for isolation of at least the line conductor, so it must break the minimum of the line conductor. RCDs, as we know, break both conductors. Maximum disconnection times, as shown in 41.1, should be applied to final circuits. Now this has changed from previous regulations. It's now 63 amps with one or more socket outlet and 32 amps supplying only fixed connected current using equipment. So have a look at 41.1. And additional requirements for socket outlets and for the supply of mobile equipment for the use of outdoors. Used to be socket outlets with a rated current not exceeding 20, it's now 32 amps, should be protected by an RCD with 30 milliamps. And mobile equipment with a rated current not exceeding 32 amps for the use outdoors. The only exception to this rule now is where, not in a dwelling, but a documented risk assessment determines that the RCD protection is not necessary. So all of the labelling or marking up of a socket outlet as not being RCD protected is no longer accepted. All circuits must be RCD protected. And now, in the 18th edition as well, there is a requirement for RCD protection on all circuits feeding luminaires within domestic household premises. Now, we've been doing that for quite some time now with the split 17th edition boards, so that's really not a big issue. Let's take a look then at the characteristics of these protective devices. So, looking at our circuit impedance, our ZS, if you look there on the formula provided, it is Ohm's law, probably written a little bit different the way you're used to seeing it. U0, of course, is the nominal AC voltage, and IA is the current flowing in the circuit. So ZS times IA must be less than or equal to U0 times, we have a factor here, C min. Now, C min is a factor that we apply to allow for voltage variation. So for low voltage supplies up to 1000 volts, C min is 0.95. So what we would do is we would take our 230 or 400 and multiply it by 0.95. That would be our voltage figure that we work with. The rest is straightforward Ohm's law. I equals V over R, or V equals I times R. All ZS's must comply to this in order to break the circuit in the right amount of time.
Right, let's just have a look at our primary earthing arrangements, because every single system using ADS will require this. So we've got a drawing here. It's a much better demonstration of the drawing than the one shown in definitions that I showed you earlier. So our earthing conductor, that's the main conductor coming from the supply head to our main earthing terminal. Now, main earthing terminal is the central earthing point of any installation, and all readings should be taken back to the main earthing terminal. Then, of course, up the top here, not a very good illustration, but that's the CPC, the circuit protective conductor. And of course, to the water and gas, we've got our main protective bonding conductors. This will almost certainly in some way or other crop up in the exam, so be prepared to be able to identify those individual component parts of that circuit. Now, double insulation or reinforced insulation. This is, we see a lot of equipment such as luminaire systems, other current using equipment and assemblies, control gear. The common one being things like power supplies, laptop power supplies, etc., which use double or reinforced insulation. Items of equipment that we call Class 2 equipment. Where it's intended to use double or reinforced insulation as the sole protective measure in an installation, it must be under effective supervision in normal use, and it must be so that no change can be made that would impair the effectiveness. But normally, one of these units would be plugged into a socket or provided with some form of ADS as additional protection anyway. Now, CPCs, plastic conduit. There's some changes with regards to use of plastic conduit, which we'll be discussing shortly when we start looking at fire and thermal effects. But a CPC must be run and terminated at every point in a wiring assembly. This is just a bit of future proofing, because if a class 2 piece of item of equipment is being used, of course, that doesn't require an earth, then it simply just terminates at the nearest junction box, the connection box. Bit of future proofing. You never know, you may be adding a class 1 item later. Then of course we can look at electrical separation. Simple basic salve system shown here, where we've got the outer exposed casing connected to earth, and we're using a transformer. Now this is an isolating transformer, 230 in, 230 out. It gives us some shaver sockets have 110, various other options, but it isolates the incoming supply to the outgoing service. So should our user, we've got a little razor there with a fault on it, if a fault developed on the secondary side of the salve circuit, there is no connection to earth. So there is no circuit there down to the radiator which is connected to earth. Then of course we've got other salve sources. We've got motor generator sets where a motor would drive a generator to create a potential, or we can provide separated extra low voltage by something simple as using a battery, or an engine to drive a salve generator. Lots of different options there. Salve, of course, remember, being below 50 volts. Now then, I mentioned it earlier, additional protection. Let's have a little bit closer look at this, 415. In addition to basic and fault protection, we have requirements for additional protection. And this can be due to certain external influences or certain locations, special locations, requirements in order to protect the end user. And the protection can be provided by RCDs specific for requirements and by the use of that supplementary bonding. So let's take a look at that supplementary bonding, the requirements for supplementary bonding. When do we need it? How do we know we need it? Now, we're told that 50 volts is the maximum safe touch voltage before any harm can come. So we need to calculate the resistance based on how much current is going to be flowing, limiting the voltage to a limit of 50 volts or 120 volts DC. So for instance, if we're looking at how much current to trip a 30 milliamp RCD, then simple Ohm's law, volts over current, will give us our maximum resistance. 50 over 30 milliamps, of course, 1,667 ohms. Simple as that. So the supplementary bonding needs to ensure that the maximum resistance is 1,667 ohms. Quite high. There are, of course, other requirements built into this for additional protection. We use RCDs with a rated residual operating current not exceeding 30 milliamps, and the operating time should not exceed 40 milliseconds when a residual current of 5 times, so 150 milliamps, is recognized in the system. This is where testing starts to come in, which we'll cover in a bit more depth in part 6. But when we test a typical 61009 RCBO or a 61008 RCD, we are looking for them to trip on the 5 times test in less than 40 milliseconds. And this is recognised in AC systems as being acceptable for additional protection in the event of failure of the provision for basic protection or carelessness by the user. There is still the option, 417, of placing out of reach or using obstacles. This isn't a protective measure that's highly recommended, and this only provides basic protection and only really should be used in installations where access is restricted to skilled or instructed persons under the supervision of a skilled person. 418, protective measures for the application only where the installation is controlled under supervision of a skilled or instructed person. There is a little bit of a relaxation of the requirements here because a skilled or instructed person is presumed to be able to perceive the risks that they are presented with. So we can have the use of a non-conducting location or a protection by an earth-free local equipotential bond or electrical separation for more than one item of current using equipment. But remember, that's only when it's in the control of a supervised or skilled person. And where automatic disconnection is not feasible, we can use such as electronic equipment with a short circuit current installed. There are provisions now. There's a couple of new regs, 419.2 and 419.3, about where required disconnection times cannot be achieved. Let's just have a look at those. 419.2, for installations with power electronic converters with nominal voltage greater than 50 volts AC or 120 volts DC, and where automatic disconnection is not feasible, the output voltage of the source shall be reduced to 50 volts or 120 volts or less in the event of a fault between live conductors. So the electronic equipment should itself regulate the voltage back down to 50 volts. And the power electronic converter shall be one that the manufacturer gives adequate methods for initial verification and testing of as well. 419.3 says that, except where regulation 419.1 applies, ADS, that if automatic disconnection cannot be achieved in the time required, then supplementary protective equipotential bonding shall be provided. So you may still see the requirements for supplementary bonding at this point. And the voltage between any simultaneously accessible conductive parts shall not exceed 50 volts AC or 120 volts DC. That's it then for chapter 41. As I say, part 4 is quite a big section. I'm going to split this over a couple of recordings. So thanks for listening to this section. I'll see you again shortly.